Okay, so we left off here yesterday, and we're going to take a look at, this power piping code. Not only does it have stuff for determining minimum thicknesses and maximum level working pressures, but it talks about supports. And so what we want to do is make sure that the pipe is supported at regular intervals. So for example, we want steam pipes to have a certain amount of slope, and that's grossly exaggerated, but we want it to slope toward a steam trap so we can collect water and we can discharge it. And we also want that steam pipe to be supported at regular intervals, because if the supports are too far away, then what we get is this sagging pipe. So here my supports are way, these supports are like 500 meters apart, okay? These are way too far apart. And what happens is in between our steam line is sagging, and what do we get? Condensate. And we don't want that. And so one of the things that we do as a regular maintenance activity in the plants where you work is you will go around, walk the steam lines, and look for pipes that are improperly supported. So the hanger has broken, maybe the pipe has fallen off of its roller support or something like that. And this is one of the things we're going to do to make sure it remains supported properly to prevent condensate from pooling and our nemesis, the evil water hammer, which blows up pipes, destroys equipment, and kills people. So we don't want water hammer. So the B31.1 says, hey, you got steel piping. This isn't actually mandated, but it's a suggestion. And the fact that it's in the code means that it's a pretty good rule. And so notice that when I've got a small diameter pipe, it needs to be supported at a particular interval. And when I get to a big diameter pipe, that spacing interval increases considerably. And the reason for that is simply because a 12-inch pipe is a mega heavy-duty, robust piece of equipment that's less likely to sag than, say, a 1-inch or 3/4-inch pipe. Okay, the 1-inch pipe is kind of like a limp noodle, and it needs to be supported at more regular intervals than if it was, say, a 12-inch pipe. So what happens if we've got, say, some pipe runs? Okay, so I've got these like flat supports, and I've got some threaded rod going to beam clamps, and I say I've got a 4-inch pipe being supported there, and I've also got, say, a 1-inch pipe along the same supports. So I got the 4-inch and the 1-inch pipes are both on the same tray, if you will. Well, then what we do is we set the interval, the spacing between those supports, to accommodate the smaller size of pipe. Okay, so we just accommodate the weakest of the pipes. There's an anchor. Okay, we know about anchors, we saw the video, so I'm not even going to talk about anchors and guides. I think those videos that we looked at did a really good job of that stuff, so I'm not going to go over it anymore. You can rewatch the videos, those little 1-minute videos. And that's it for piping. You should know the purposes. Why do we have steam traps? So, of course, we want to discharge accumulated condensate, but we also need them to vent non-condensable gases. Those non-condensable gases are air on startup and also CO2. And some people might wonder, well, where the heck is the CO2 coming from? Let's say we've got a sodium zeolite softener, Na2Z, and what happens is we've got dissolved solids, scale-forming compounds, enter into the sodium zeolite softener. And so let's say that happens to be magnesium bicarbonate. MgHCO3 twice. And what we end up with is the non-scale forming compound. We end up with 2 NaHCO3. That's right. Yeah. Well, that's sodium bicarbonate. That's baking soda. It doesn't form scale in the boiler, but the bicarbonate decomposes in the boiler to form CO2 gas. And if you recall, in the condensate lines, the CO2 forms carbonic acid and rots away at the condensate lines. But regardless, it is a gas, and we still have to deal with it in the steam system. What we have to do is we've got to vent it. And then the last thing that the steam traps are going to do is they're going to prevent steam from entering the condensate system. So let's take a look at some of the various, let's just take a look at this again. Let's go back here to number 1, discharge accumulated condensate. What happens if we don't? Well, we're going to get water hammer, okay? And so water hammer occurs whenever we've got saturated liquid and saturated gas together in that same pipe. Now then, the next thing is we want to prevent water from entering machinery. So let's say the condensate is a slug of water upstream of a turbine. Break the turbine. Now, promoting heat transfer, if we don't remove condensate, so let's say I've got a heat exchanger here, and I'm going to put some steam in there, and it's a shell and tube heat exchanger, so I've got a whole bunch of tubes. And that steam is going to condense, and it's going to give off its latent heat, and then we want the condensate to leave. But what happens if we don't remove the condensate as it forms? The condensate builds up and builds up, and so that instead of having 100% of the heat transfer surface in service, we end up with 70% of the heat transfer surface in service, and then 50, and then 40, and 30. Before you know it, we got this thing full of condensate, and it's just not transferring heat the way we want it to. So we want to maximize the heat transfer surface all the time, and if we're not removing the condensate, we are going to diminish the heat transfer. Now, what do they do with the condensate? To some kind of recovery system, and maybe we could add this as an altogether different thing, but you see, condensate recovery is very important because it's basically pure water. As such, it makes very good boiler feed. So we want to recover it. Plus, not only are we talking about recovering material in the form of pure water, okay, but we're also going to recover some of the heat in that pure water because it's going to be fairly hot condensate. And we are also going to reduce our water treatment costs. And the water treatment cost is a lot of things. It's the cost of water, because we've got to pay for it. It's the cost of chemicals to treat the water. So the more we recover, the better we have it. So we try and recover as much condensate as possible and put it back into the boiler. Now, as for this venting air and non-condensable business, again, we've got our heat exchanger, just looking at it on an end view here. And if I end up with, okay, I gotta make air. Air is going to be blue, okay, because we know air is blue. Because when you look out, the sky is blue, so air must be blue. Am I right? Of course I'm right. So we've got all this blue air in there, and we know that steam is red because hot things are red, and so steam is hot. Okay, so it's red. Anyway, so we got this air and steam mixture inside of this pressure vessel, inside of this heat exchanger, and what we find is it's not as hot as it's supposed to be because the air is occupying a big chunk of the space. And air is also non-condensable, so even if the air is hot, it's not going to condense and give off latent heat. When we have got air and non-condensable gases in our steam system, they occupy space and they inhibit heat transfer. So we got to get rid of the air. So that's number 2, is getting rid of air and non-condensable gases. And then 3 might sound kind of silly, prevent steam from entering the condensate system. But let's go back up to this heat exchanger here. Here's my red hot steam going in, and it's transferring heat through the heat transfer surfaces. And, well, what if we didn't even bother with the steam trap? Well, then we'd have steam just blasting out. Yes, we would be heating up the transfer fluid. Yes, we would get good heat exchange, but we have not used all of the latent heat in the steam. We want to confine the steam inside of the heat exchanger with a steam trap, and that's why we call it a trap. By confining the steam, we maximize the latent heat extraction from the steam inside of the process vessel, and all we end up putting out is condensate, which of course does not have that latent heat. And we know latent heat is such a big thing with steam, right? That's why we use it. It's such a wonderful heat transfer fluid. So that's the long and the short of it, of why we have steam traps and what do they do, and why we need them. And I'm not going to go into too many details, except we're going to take a look at some of those operating principles in detail and see how each one of these traps maximizes and works on those particular concepts. So here's a steam main, and the steam's going that way, and we got a heat exchanger over here. So where do we put them? Well, we put them where we got a steam separator. So let's say I've got 95% dry and saturated steam going into the steam separator, and leaving the steam separator, maybe I've got 98% dry and saturated steam. Well, what happens is the steam separator is going to get a little bit of liquid buildup in it, which we want it to do. So we're going to put a trap, and we're going to discharge the condensate from the steam separator. Very good. Now here we've got a reducer, and reducers are pretty interesting because there are lots of different kinds of reducers. So let's say we've got a 4-inch NPS4 over here, and here we have got a 2-inch steam pipe. And so we have this rid fitting. And I got to tell you right now, we don't want to do that because condensate is going to form a pocket right down there. So that's kind of no good. What we really want to do is this: take a 4-inch and have an eccentric reducer. It's a little bit of a different fitting, and so instead of having the pipes on a common center line, what we have is the 2-inch pipe is down here, center line, 4-inch pipe center line's a little bit higher, and what we have is a smooth bottom that will not collect condensate. But that being said, you will find concentric reducers in your piping systems on your steam lines, and you're going to go, who is the idiot that put a concentric reducer there? That's wrong. But if they are there, you can solve it by sticking a trap over here where the condensate could collect. Doing okay? Now, we usually have one, we'll say before the expansion joint. Here's a bellows type of expansion joint, and you know that they're made of a corrugated bellows. And the last thing we want to do is have water sitting down in the base of the bellows. So if we can collect the water before the bellows and discharge the condensate, better situation for us. Where else do we find them? Here's a riser. And at the base of a riser, we are going to have this thing here that we call a drip leg. And that's terminology you probably should know from last year, but if you don't know, now you know what a drip leg is. And at the base of the drip leg, we're going to put a steam trap because, of course, as this pipe warms up, it's going to form a lot of condensate. And even just in normal operations, of course, there's going to be heat radiating. Even though it's an insulated pipe, we will see heat radiating from the pipe, and we're going to form condensate. And we got to grab it at the low point, which is the base of the drip leg, and again we discharge the condensate. Now here's one, a control valve, or we could even say a regulating valve. So maybe we got a steam pressure regulator. Just upstream of it, we're going to have a control valve, or pardon me, yes, just upstream of it, we're going to have a steam trap. So here it happens. Think of this control valve as being on-off. So it's either going to be open or it's going to be shut. Now, I know that those would be sort of the extreme conditions, you know, in terms of its modulating action. Maybe it's fully modulating. Maybe it is an open shut. Maybe it's a solenoid valve. I don't know. But regardless, it is some kind of a control valve. And when that valve is shut, okay, what's going to happen is the steam is going to be deadheaded before the valve. Condensate will build up, and then when the valve opens again, we're going to get a slug of water that goes down that pipe, and it's going to cause water hammer. It's going to break valves and knock off elbows and all this kind of bad stuff. Then over here we have an isolation valve, and you've noticed this. So let's say, you know, if you're starting up the steam turbine powered boiler feed pump, you'll notice that there are steam traps that are positioned just upstream of the isolation valve. Again, what we have is a situation where condensate will build up in this pipe, and then if I open up that valve, I'm going to have this slug of water going bang and wrecking the downstream equipment. Well, we don't want that. So because we know that that isolation valve may be closed at certain times, we want to have some way that we can collect that condensate and drain it out on an ongoing basis. And then the last thing here, you know, where there's a heat exchanger, yeah, so, you know, we want to confine the steam inside of the heat exchanger, and we want to vent air out of the heat exchanger, and we want to make sure only condensate leaves the heat exchanger, and but we also have to remove the condensate as it builds up. So yes, in heat exchangers, but also if you think of another piece of equipment that we might have that you folks are running, we've got a steam turbine. And the steam turbine has casing drains at various locations to prevent condensate from building up inside of the casing and demolishing the rotating blades. So here are just some of the places where we put them and why we put them. Okay, so now as for operating principles, we mentioned in that Kahoot thermostatic, mechanical, and thermodynamic. So this is a little bit of a different approach. What we have is a sensing element. And so think of instrumentation, think of a primary sensing element, and think, what is that sensing element sensitive to? And as for a thermostatic trap, we've got an element that is sensitive to a temperature difference between steam and condensate. Now that is a bit of a problem. And the reason it's a problem is you think of steam and condensate being at the same temperature. So if I happen to have steam, come on pen, work for me. If I've got steam at 200 degrees Celsius and that stuff condenses, what do I end up with? I end up with water, condensate at 200 degrees Celsius. Well, how can you have a thermostatic trap that is somehow sensitive to a difference in temperature? Well, there is no difference in temperature. 200 is 200, whether it happens to be steam or whether it happens to be water or condensate. So in order for a thermostatic trap to work, the condensate has to cool off. It has to become subcooled. So maybe then we have a trap that opens at 180 degrees Celsius. Okay, so that is the temperature difference that a thermostatic trap works on. It works on this whole notion that condensate must subcool for there to be a difference in temperature between it and the saturation temperature of the steam. Now it can actually differentiate. Is there steam present or is it only condensate? Well, it's a 20-degree difference in this example. Now, as for the mechanical type of trap, what we have now is one that is sensitive to density difference. And so how does that work? Well, we have some kind of a chamber, and the condensate builds up in the chamber, and we'll put a float there. The float registers the interface between the steam and the condensate. And as the condensate accumulates, the float then responds and opens up a valve to discharge the condensate. So mechanical ones are sensitive to a density difference. And as for the thermodynamic, it's sensitive to differences in energy between the steam and condensate. We'll go a little bit more detail in that as we go along here. Okay, so here's all thermostatic traps, and so I'm going to use red here, indicating that it's thermostatic. So what we're going to look at is a bellows type of trap. We're going to look at the liquid expansion trap. We're going to look at the bimetal trap, and we're going to look at the balanced pressure trap. Now, of these, the balanced pressure trap is not in your Pan Global, but it's very, very important, and you need to know about it. Also, the liquid expansion trap will be new to you, but that one is in your Pan Global. Both of these are related, okay? They're related to each other. And if we take a look at the pictures, this one here is the one that's in your Pan Global. Maybe not that picture, but that is the liquid expansion. And this one over here is not in your PG, but that's the balanced pressure. And then this one here is the radiator trap. And what all of these have in common is they all have some kind of a bellows or a pressure capsule. So keep this in mind. If a trap has a bellows, it is susceptible to water hammer. If water hammer occurs in the body of the trap, it will destroy the trap. And I'm back to writing with my mouse. So water hammer sensitive. Okay, I got to find a smaller word because otherwise it'll take me an hour to print it out with my mouse. Now, the bimetal is another type of thermostatic trap that in fact is not water hammer sensitive. So we'll take a look at those ones too. And we'll clarify some of the misconceptions about those. So here is the basic radiator type trap, bellows trap. And I don't think I need to go over this much, right? Okay, so what we have is some kind of a fluid inside of that bellows, and that fluid expands when it's hot and it shuts off this valve down here, and when it's cold it contracts and opens up the valve. So cold means condensate because it's been subcooled, and hot means it's surrounded by steam, which is at saturation temperature. Now, very simple trap, but like I said, it's got a bellows, so susceptible to water hammer. It's fairly easy to service because there's a bonnet here, so it's threaded, and you can unthread and you can pop out the pressure capsule or the bellows, and you can replace that for a certain amount of money, but it may not be worth it. You might just replace the trap altogether And then it does have a removable seat down here, which is also threaded. So maybe the more expensive ones are serviceable, but the smaller ones are just kind of like throwaways. Now, this bellows here, does this trap fail open or does it fail closed? And the answer is yes. It fails open or it fails closed, one or the other. And it depends upon the kind of bellows. As a matter of fact, you usually, when you buy these things, you have to order the type of bellows. You have to specify, do you want it to fail open or do you want it to fail closed? Failing open is usually the most desirable thing. Better to waste steam and energy than to have condensate backup. Now they're always positioned with the orifice at the bottom, which means that they tend to drain automatically, which is kind of a good thing because if it happens to be in a cold environment, less likely to freeze up. And that's basically our radiator or bellows trap. But this one here is similar. It's got a bellows. This is the one that we had in the Kahoot yesterday. Now this one here is filled with a liquid. It's oil, some type of an oil that has a particular coefficient of volumetric expansion, beta. And so when it's surrounded by hot condensate, it closes. And when it's surrounded by cool condensate, it's open. So let's just take a look. We've got condensate coming in. The condensate's cool, so it opens. But then hot condensate comes in, and it closes. Okay, cool condensate comes in, it's open, and then as it heats up, it closes. And then the condensate goes out there. So the bellows is always immersed in condensate. It's always going to be radiating heat. So the condensate subcools, and when the condensate subcools, it opens. And it discharges condensate. It has a variable set point from 60 to 100 degrees Celsius. That's from the Spirax-Sarco website. As a matter of fact, this particular one here is a Spirax-Sarco design. And notice that it has an adjustment nut at the end. So by adjusting this, we can actually control the discharge temperature. We can set it between 60 and 100 degrees Celsius, which is a real problem because we're going to take a look at this one here. It's got a slide. Let's say that we have it set to 90. Okay, so this one's going to be set to a 90 degrees Celsius discharge temperature. Oil has a known coefficient of volumetric expansion. And so what that says, it has a fixed temperature response line. It will always discharge at 90 degrees Celsius. But if we take a look at steam, steam's a little bit different. Steam has a temperature, saturation temperature, that varies with pressure. So as steam pressure increases, the saturation temperature increases. So this line here is our steam saturation curve. Okay, increasing pressure, increasing temperature. So let's say we're down here at P1. Maybe this is, I don't know, 150 kPa. At 150 kPa gauge, we've got condensate forming here at, say, I don't know, 115 degrees Celsius. That means we've got particular delta T, and so it has to subcool from 115 degrees Celsius to 90 degrees Celsius before the trap actually opens. So condensate is going to be this warm, and then the condensate has to cool off below 90 before the trap actually opens. So the subcooling then would be, what, 25 degrees of subcooling has to occur. So let's imagine that this steam line is warming up. So it's at 150, but let's say normally it runs at, let's say this is 1000 kPa. At 1000 kPa, the temperature of the steam, and I'm just making this up now, let's say that the steam temperature is 200 degrees Celsius. Totally making this up because I don't have steam tables in front of me. But you know, I could look it up if I wanted to, but I'm not gonna because I'm lazy. So we're just gonna pretend that it's 200 degrees Celsius, condensate forming at 200. Well, that 200 degrees Celsius condensate has to cool off all the way to 90 degrees. That means it has to lose 110 degrees Celsius until it gets subcooled to 90. Well, what's happening during that period of time that it's cooling off? Well, I'll show you what's happening. Here's my trap. It's discharging at 90 degrees Celsius. Condensate is coming in at 200 degrees Celsius. And it has to radiate a lot of heat. Well, while it's busy radiating heat and lowering its temperature to 90 degrees Celsius, condensate builds up and builds up and builds up. Here's my drip leg on the pipe. And the condensate builds up and builds up and builds up and builds up and it backs up like crazy. What we want to have is a steam trap that is responsive to the saturation curve. If it's going to be a thermostatic trap, then how about we have one that follows that curve so that the subcooling doesn't matter what the pressure of the steam is, we always have the same amount of subcooling. That would be the desirable one. But this one here, nah. It's kind of a bummer because it's got this low fixed temperature. And why does it have the low fixed temperature? Because it's filled with oil, and because oil has a specific coefficient of volumetric expansion. So this type of trap is never used when we need immediate condensate removal. But what we can do is we can use it as a startup trap and we can use it as a shutdown trap. And that's where we see it. So here's our steam main. We got steam flowing through it. And during startup conditions, we make a lot of condensate. Maybe we make so much condensate that this poor little trap here is overwhelmed. But the condensate is going to be relatively cool. When we first put steam in this line, the condensate is going to be 100 degrees Celsius when the steam main is at 100 degrees Celsius. So in other words, when we're just filling it up with steam, we're making lots of condensate. The condensate is pretty cool. We're going to discharge at 90 degrees Celsius. So the liquid expansion steam trap is going to be great for us. It's going to pass a lot of condensate that forms, and it's going to help out this poor little trap over here. Then as the steam pressure increases, and so does its temperature, so maybe we're at 150 degrees Celsius, then we're going to have condensate at 150. This trap here is going to start to back up condensate because of the subcooling that it requires. And as it backs up condensate, this trap comes into play and handles that condensate alongside this one here. And what we find is once the steam line is in full operation, so let's say that the final steam temperature is, say, 180 degrees Celsius, both traps will remain in service. This one here, intermittent discharge. It will only open after that 180 degree condensate is cooled off to 90. Intermittent. Whereas this one here will have regular discharge. So that's when we're up to normal pressure and temperature. Now, when we shut down the steam line, the opposite occurs. It cools off. We still have to deal with condensate. And once that condensate cools off to 100 degrees Celsius, the liquid expansion steam trap will open up fully and drain condensate like crazy. So, to summarize, when do we use these? We can use it in combination with another steam trap that is not a liquid expansion type, and we can use it for startup, a startup trap. We can call it a shutdown trap. I've gone into far more detail than the Pan Global goes into because the Pan Global, as far as I'm concerned, will just leave you with questions, and hopefully this has answered some of your questions. Now, the balance pressure trap is the same as a liquid expansion, except for two things. Number one, it doesn't have an adjustable discharge temperature. And then the second thing is the bellows inside of it, the pressure capsule, is filled with a volatile liquid. So because the liquid is volatile, it will respond to the pressure and temperature of the condensate. So that's the pressure capsule right there. And that's our temperature sensitive element. Here's how it works. We get some right now cool condensate. So it opens up, and then it discharges until hot condensate surrounds it. And then after it cools off, it opens again. Now, as for the response line, this one, in fact, does have a response line that kind of corresponds fairly closely to the steam saturation curve. So it doesn't matter whether we're at low pressure warming up the pipe. What we then have is, I don't know, 15 degrees of subcooling. And as the pressure in the pipe increases and the saturation temperature increases, again, we've got a 15 degrees Celsius subcooling. You get the idea. This one here actually responds to the steam saturation curve because, why? Because it's full of a volatile liquid instead of an oil with a fixed coefficient of volumetric expansion. So some people call this the improved liquid expansion trap. I'm going to skip that slide. Now the next is the bimetal, and the Pan Global kind of slags this. What Pan Global says is, oh, the bimetal is weak, and because the bimetal is weak, it doesn't close very well. It doesn't shut off tight. And who wants a steam trap that doesn't shut off? I mean, part of their job is to trap the steam until it gives off its latent heat. But if this one here is passing all the time, that's no good, right? So who wants it? So here's the idea. What we're going to do is put a whole bunch of bimetals there, back and forth. And now having multiple bimetals will give us two things. It gives us a greater distance of travel of the plug. So more bimetals, we get a greater back and forth opening and closing action because we amplify the small flexes of the bimetal strips. So now we got greater range of motion, and we also have a more closing power. Now here's our steam saturation curve again. And one of the things about a bimetal is bimetals also have a flat response curve. Actually, I'm going to redo that one. Pardon me. They also have a flat response curve. Ignore the first line that I drew. And what we find is at low pressures, the saturation temperature will be below the closing pressure of the trap, the closing temperature of the trap. So we actually blow steam at low pressures. But then after a little while, we got sort of this reasonable subcooling effect, but the subcooling effect requirements increase as the pressure increases on the trap. So again, Yes, we can do something about it being weak and about it not shutting off very well. We can do something about that, but we can't do anything about this flat response curve. So what will happen is it's going to back up condensate just like the liquid expansion did at higher pressure. But what we can do then is, let's say we have these bimetals are of composition A, metals A and B, and we got these other ones here are of different composition, metals X and Y. And so they both will operate differently, I guess. So what we can have then is, if this is our saturation curve, we can have metals A and B are like that, and metals X and Y are like that. So what we end up with is this kind of crude following of the saturation curve of the steam. And the net result is less likely to back up condensate. So here's a real trap. This is from Spirax-Sarco, and we have all of these bimetal discs, and they're all stacked up, and they all provide force to move the plug up and down. And I'm just taking a look at these. They likely have different compositions so that they more closely track the steam saturation curve. Beautiful. So now what we have is we don't have any, pardon me, they don't have a bellows, so they withstand water hammer. Water hammer is not going to crush a bellows. They're fully open when they're cold, so they're good at venting air. They're good at dropping a lot of condensate. They may back up condensate, but if it is a multi-bimetal type of design, it probably shouldn't. But just to be on the safe side, let's have a pretty big drip leg. Okay, the bigger the drip leg in the steam pipe, the more condensate can accumulate so that the trap, a slow responding trap, has a chance to kind of catch up to condensate load.